So, and it's weird for those of you that are taking the AP test, sometimes they like hammer this whole concept of intermolecular forces, and sometimes they just briefly might have one or two questions on it. It's just kind of weird. So, if you look on question number 12, and it has kinetic energy of molecules compared to the average energy of attraction. So this is basically, if you look at something whether it's a solid, liquid, or gas, you have two competing parts. You have basically the kinetic energy that allows Timmy to bounce around as the crazy little kid that he is. And then you have the energy of attraction. And these two things are basically at battles with each other. So, conveniently, we have a universe where neither one of them is like completely, totally dominant. Because if atoms didn't have the ability to form bonds, and it's tough, it sounds simple, but it's very profound. If atoms didn't have the ability to form bonds, we wouldn't be here. Okay? We exist solely because we live in a universe, number one, that has electrons, protons, and neutrons. If the universe had only made electrons, if the only had made protons, or if the universe says, hey, I'm just going to make positive and negative charges, great. If we didn't have neutrons, we wouldn't be here because we would not be able to basically even form helium. We just have hydrogen. Cool, right? That's it.
Nuclear decay shoots out neutrons, right?
It depends upon the type of nuclear decay.
Let's say
there's alpha decay, there's beta minus, there's beta plus, a whole bunch of different types.
Will we go in that or not?
We will in physics.
Okay, good.
What do those two, AJ and E?
Okay, so this is kinetic energy.
Yeah.
Okay, and this is the energy of attraction. Right? So we have all three of these. And one of the things that we struggle with is like, it's cool that we have an equal balance of them, but the other weird thing about when the universe began, if you look at what's the square root of 4? 2. Or minus 2, plus or minus 2. So what should have happened when the universe was created, and you start with pure energy and then you create matter out of that, is that there should have been equal amounts of what we call matter and antimatter. Okay, antimatter has the exact same properties of normal matter, but it has like the opposite charge. So in antimatter, you have what we call positrons instead of electrons. So they have the exact same mass, everything is the same except they're positively charged. Protons are negatively charged, same mass and negatively charged. So you just basically flip the script. Problem is that when you have matter and antimatter, as soon as they run into each other, they annihilate each other and it goes back to pure energy. So if the universe had made completely equal amounts of matter and antimatter, we wouldn't be here having this discussion. But something shifted it. We made slightly more matter than we made antimatter, and that's why we're here. So not only did we make what we consider to be matter, okay, that matter had the ability to form bonds. The ability to form bonds is what allows us to be here. So the bonds exist because of this battle. So when you look at solids, okay, and if you think about this, most of your interactions with the world around you is solids, okay? Your shoestrings, your shoes, your clothes, okay? Your car. Driving a liquid car would be tough, okay? You turn, no, we just ooze. So you have a lot of things that are solid. We have an atmosphere of gas. Without that, we wouldn't be here having this discussion. The gases exist because the kinetic energy part of this is much stronger than the attractive part. This is why it's a gas. This is why nitrogen and oxygen that make up our atmosphere exist as gases. They run into each other, and this is what we're talking about today, is the ideal gas law, and they bounce off. Okay, they act like tiny, tiny little like ball bearings that bounce around, and every time they have an interaction, we assume that they don't lose any energy. Isaac?
Okay, there's a question on the thing I was confused about. For liquids, are they equal?
Yes.
Okay.
That's what I was thinking.
Okay.
So gases are very much favored on the kinetic energy side. Solids are very much favored on the attractive side. Liquids kind of have a 50-50 split between the two of them. So liquids are kind of like this middle ground. They're held together enough that they can move past each other, but they're not held so tightly that they're locked in place. So this is kind of this middle ground between the two of them. That's a generalization, it's a huge generalization, but that pretty much works, okay? And even within that, you have different degrees of binding energy. Diamonds, incredibly hard, okay? And here's the cool thing about when you look at even carbon and the arrangement of carbon atoms. If you're writing with a pencil, okay, graphite is basically a sheet of carbon atoms. So if you arrange carbon atoms in sheets like that, you can write with it. So when you write on a piece of paper, if you look at what happens on an atomic level, you're basically tearing atoms of carbon off from the graphite. And it's sticking to the paper. So the attractive force between the graphite and the paper is stronger than the attractive force between the graphite within the carbon atom. But it sticks there. And you know that because it isn't like you go to hand in your paper and you lift up your paper and all of a sudden all the graphite falls off of it. Like Burkamp, I swear to God, I had the assignment done. The graphite didn't stick to my paper.
Carbon bonds with paper.
Yeah, carbon bonds. Somehow or another, we lost those bonds. I tilted it up, and there was just this pile of graphite on my desk. Yes.
Would it be possible to invent a piece of paper that goes
That would be
Yeah, it's called wax
I
paper.
want to pick up all the little words.
What?
Like,
No. Okay. So that's relating to question number 12. Okay, when you're going to rank those things. Now, the second part of 12, it says, why does increase in temperature cause substance change in succession from a solid to a liquid to a gas? So what's happening is that you're not going to alter the attractive force between the particles. It's like butter, okay? Butter coming out of the refrigerator is pretty solid, right? You want to melt the butter, what do?
Put it in the microwave.
Put it in the microwave. So here, this is an important distinction. Does melting the microwave weaken the bonds between the butter molecules?
Melting the microwave?
No. Just asking a
Okay. No, hold on. This is an important distinction. So you want to melt butter. Does the microwave weaken the bonds between the butter molecules, or does it give it more kinetic energy to overcome those bonds? Yeah, it gives it more kinetic energy. So the same thing is going to happen if you want to boil water. You want to boil water. Okay, here's all these water molecules. Great. So when you're putting in that, heating it up, you're making these things vibrate more and more and more until the kinetic energy part of it overcomes the attractive force of it, and then it begins to boil. Now, another way that you can talk about the strength of intermolecular forces is something called vapor pressure. Okay? So, see if you, Nathan Nelson, see if you can find this. See if you can find me the vapor pressure of methyl alcohol.
.8 to 16.9 kPa.
What was it?
12.8 to 16.9
12.8. What units was it?
kPa.
Kilopascal. Now, see if you can find me vapor pressure of ethyl alcohol.
.67.
13.7.
Yep.
Okay. Now, So when you talk about what we call vapor pressure, so vapor pressure is measured based upon, you take a cylinder.
Well, are we assuming room temperature?
Yes.
Okay, it's 7.87.
Yeah, that's,
7.87.
that sounds better, because otherwise, I was gonna say, your data source is wrong, because they broke physics. Okay, so how you measure vapor pressure? Oddly enough, you take a pressure sensor, and you put some of that liquid in the cylinder, and what's gonna happen is that some of this stuff is gonna break free. And oddly enough, it's gonna turn into a vapor, and that's gonna create pressure, hence the term vapor pressure. Okay? So methyl alcohol has a vapor pressure of 12.8. Ethyl alcohol is 7.87. So another way that you can look at the strength of the intermolecular forces is the amount of vapor pressure. So methyl alcohol's vapor pressure is higher because if you look at the structure of methyl alcohol, that's CH, boom, boom, OH. Ethyl alcohol has 2 carbons. Those are hydrogens, and an OH group. So here's the conflicting thing. So ethyl alcohol, find me the, while we're on here, find me the boiling point of ethyl alcohol.
.2 degrees Celsius.
Okay, find me the boiling point of methyl alcohol.
Let's do an ethanol, bro.
It's the same thing. Ethanol and ethyl alcohol are the same thing.
Okay, and for what?
Methyl alcohol.
$64.7.
64.7. Okay, so this, you should be able to look at this data, and this should make sense. So methyl alcohol has a lower boiling point. So what that means is that it's easier to overcome that attractive forces between the methyl molecules than it is the ethyl. So how do we account for that difference? Well, if you look at this structure, you have 2 things going for you. Number one, methyl alcohol is spiky. Okay, it looks like this. Okay, in a very crude manner. It looks like this. Methyl alcohol, you would look like this with an OH group on it. Okay, so this is longer. There's more molecules. There's more electron clouds. So you have 2 things that are accounting for the difference in this boiling point. So the ethyl alcohol has a higher boiling point. This is a horribly non-scientific term, but it makes perfect sense. This is stickier. Okay, these molecules are stickier. They have hydrogen bonding. They have London dispersion forces. They have a dipole moment. Okay, that's why it exists as a liquid at room temperature. Methyl alcohol also has all of those, but methyl alcohol won't have as strong as London dispersion forces because of the fact that it's a smaller molecule. So here's the diversity between these 2 measurements. And this is one of the things you have to understand. So boiling point, the higher the boiling point is, the stronger the intermolecular forces are. Okay? So with boiling point, as you increase the boiling point, there's a direct relationship between the strength of the intermolecular forces. So if all you're given is a chart of boiling points and say which one has the strongest intermolecular forces, pick the one with the highest boiling point. Now, vapor pressure works the opposite way. Okay? So the vapor pressure for methyl alcohol is 12.8. The vapor pressure for ethyl alcohol is 7.87. So the reason that these go in opposite directions, but it's the same idea. So it's easier for methyl alcohol to go from the vapor, from the liquid into the vapor. So at equilibrium, that vapor pressure is higher because it's easier to break the bonds that hold those things together. So with vapor pressure, as vapor pressure goes up, your London or your intermolecular forces go down. So there's an inverse relationship in terms of vapor pressure. Now if you think about, oh, what makes vapor pressure? Oh, it turns into a vapor. So the easier it turns into a vapor, the higher the vapor pressure is going to be. So like the vapor pressure of concrete, pretty much zero, okay? We don't have to worry about concrete turning into a vapor, right? And that's okay. Like what happened to the floor? I don't know, turning into a vapor. Weird, okay? No, your skin, you don't have to worry about that turning into a vapor. It's okay. All right. Now, when you get to like question number 20, so 20 is kind of the quintessential summation of all of this stuff. So when you get to 20, you've got the acetone, and then you've got the, that you're comparing all of these questions. And so what you want to look at is this in terms of the CH3OH boils at 65. The CH3SH boils at 6. Okay? So here's the story. Which one has the higher boiling point on 20A?
CH3OH.
So no matter what happens, that has the higher boiling point. So you know that whatever forces that hold them together have to be stronger than the other one. So what's the fundamental difference between those two molecules on 20A?
The OH group, hydrogen bonding.
Yeah, the one that has the hydrogen bonding, because hydrogen bonding tends to be pretty strong, which is why we have liquid water, okay? So you're going to say, oh, okay, right. So on that one, the CH3OH, it has hydrogen bonding. You don't have to say that, but that's, that's kind of the whole point of this story. So, and it says which type accounts for this. So when you get to B, you have xenon and you have argon. Okay, so let's talk about those. Where is xenon and argon on the periodic table? Noble gases, right? Okay, noble gases. Are they going to bond with anything? No, because they're the Olivia Pruitts of the world.
They're happy.
They have the 8 game pieces. So there's a couple of reasons why noble gases are extremely difficult to find. Number one, they're very rare. Okay? Number two, they don't bond with anything. So imagine that you're at a graduation party and you have a very stuck-up roommate who doesn't interact with anyone, and there's like one of these persons for every 100 other people, okay? And a week later you're going, hey, was Bubba at the party? I don't know, seemed didn't interact, okay? So these are tough to isolate because they don't interact, because they're very rare. So the only way you can isolate them is to basically take a bunch of air and cool it down, and then you're going to see when these things begin to condense. And then you collect them because they're going to condense at different points. So here's the basic idea when you're looking at xenon versus argon. Which one has the bigger electron cloud? Xenon does. So therefore, that's going to have stronger London dispersion forces. So if you have the noble gases, the only type of bonding that can occur is LDS. That's it. And the bigger the electron cloud is, the stronger those ODS. So this is why helium is the coldest liquid on Earth. Okay? Because here's this nucleus, and you only have 2 electrons. And so that's why it's the coldest liquid. Liquid hydrogen is the second coldest. Hydrogen has 2 protons. It also has 2 electrons. Okay? But that's easier to induce a dipole moment on that hydrogen because there's 2 electrons and like kind of 2 different orbitals. Not much of a difference, but this is why helium is the coldest liquid on Earth, because it's so difficult to get it to be sticky because it's there's just so little matter to work with. Okay. So when you get to 26, and you're comparing those structures on 26, everything is basically the same between these two molecules except for what? The shape. Which one's more linear? The propyl alcohol is. That's more linear, so when those run into each other, there's more surface area, so it's easier to induce a dipole moment. For those of you that are taking the test, if you have a free response question where to ask you to compare like London dispersion forces, you would say something like it's easier to induce a dipole moment. If you really want to get fancy, you can say it's easier to make it turn into polar. You could say its polarizability is higher if you really wanted to sound fancy. Okay? So basically, you're trying to induce a dipole moment that created by a disturbance in the electron cloud. Okay. So when you get to 29, so ethylene glycol, and that's what makes the antifreeze. If you haven't ever added antifreeze to your engine cooling system, you might. And then that boils at 198, and then you have the other one boiling at 78. Okay? So explain why the replacement of a hydrogen on the oxygens by a CH group generally results in a lower boiling point. So basically, here's, in a short version, here's this. So here's one, you have a hydrogen. There's the next one, you take off that hydrogen, and you put an OH group on it. So everything stays the same except for you add an OH group. So there's two things that you get by adding an OH group. What are the two things you get by adding an OH group? You get hydrogen bonding and you have dipole. And now you have a dipole moment. So now you have two additional bonding opportunities that you don't have if it's just this. Okay? So keep that in mind. All right. Any other questions on that assignment? Going once, going twice. So